This video, we're going to talk about some advances in science and related advances in mathematics. The pictures that you see here on the left are Copernicus and on the right, Kepler. We'll talk a little bit about them in a little bit. So mathematics and the physical sciences, particularly astronomy, have long been intertwined. It's a relatively new development to think of these as separate fields. The same people that were making mathematical advances were often the same ones that were making scientific advances. In particular, trigonometry and astronomy were very intertwined. There were several important advances in astronomy that occurred during the Renaissance, including a move away from a geocentric model of the solar system to a heliocentric model. Let's look at a few key mathematician scientists of this period. First one I will look at is a guy named Johann Mueller, or known better as Regiomontanus. He was born in 1436 and died in 1476. He was born near Königsberg in Lower Franconia in present-day German. This is not the more famous Königsberg in Prussia. He was known by a variety of names. I'm not going to list them all here. He's best known by the name Regiomontanus today, and that's really a reference to the town where he's from. Königsberg, if you translate that to English, basically means King's Mountain, and that's also what Regiomontanus means. So he basically took the name of his town as his name, and that's what he's best known by today. He was a mathematical and astronomical prodigy. He studied at the University of Leipzig at age 11. Later on, went to the University of Vienna, where he got advanced degrees and was a student there, and then later on a faculty member. In 1461, he traveled to Rome, spent the last part of his life there. In 1464, he wrote a systematic account of trigonometry. His sine tables were in sexagesimal notation and also later in decimal notation. So the decimal notation was kind of a relatively new thing because you may recall from some of our earlier videos that the sexagesimal notation, a holdover from ancient Babylonian numerals, was associated with measuring fractions in astronomy and hence in trigonometry. It's where we get our degrees, minutes, and seconds relationships today. He was one of the earliest to have mathematical and scientific works printed. So he made it a very concentrated effort to get ancient mathematical works and medieval mathematical works and get those things printed so that they could be regularly available. So he was an important mathematician of the early to mid 15th century. Now we're going to talk about a very important astronomer, Nicholas Copernicus. That version of his name is the Latinized name version he went by. He's most known by that. He was probably Kopernik or something like that would have been how they pronounced his name originally in Polish, because he was Polish. He was born in 1473 and died in 1543. So he was a Polish astronomer and mathematician, and he's most famous for proposing a heliocentric model of the universe. He studied medicine, astronomy, and canon law. And at the very end of his life, in 1543, the year he died, he published his work in a work called De Revolutionibus. His work included the heliocentric model, and they were, like I said, they were published at the end of his life. There's a report that he actually got the published version on his deathbed. But something interesting happened there. The publisher added a letter to the preface indicating that the results were not to be taken as a literal fact, but rather as a computational convenience. Probably not something that Copernicus himself would have said. But it's probably fortunate that he did that, because otherwise the books were probably just been burned and we never would have had them. Because the church of that time favored a geocentric model, which had been around at least since the time of Ptolemy, and that was the prevailing thing, and the church leaders actually interpreted some scriptures in the Bible to support that theory. And of course, since they felt the Bible was infallible, they would not accept anything else. But he wrote this for mathematicians, and later folks were able to look at this and say, hey, this actually does describe what's going on, say better than Ptolemy's Alchemist did. So whether it's true or not, they weren't really as concerned with that, but rather did it aid in the calculations. He did incorrectly assume that all planet motions were circular. That's something that we will find out. I'll show you who found that out here in just a minute. But you know, a reasonable model for that, and definitely much closer to reality than what was there before. Next up, I want to talk a little bit about Tycho Brahe. He was born in 1546 and died in 1601. So later 16th century mathematician and astronomer. He was Danish, born in Denmark. And later on, he lived in Bohemia, which is now the Czech Republic. And he believed in a geocentric model of the universe. So he did not agree with Copernicus. But one thing that he did is he said, we need to make some precise astronomical observations. And he did that for over a long period of time, for over 38 years. He made very, very precise and detailed observations and kept records of all of those things. And those, in turn, helped some later folks, particularly Kepler, to make some important discoveries and theories that turned out to be correct. Very important guy here was Galileo Galilei. He was born in 1564 and died in 1642, so late 16th, early 17th century. He was Italian mathematician, astronomer, and natural philosopher. You see that term natural philosopher? That's a kind of term that became pretty popular about this time, and it you know, today we would probably call him a scientist slash mathematician, but that was a term that was used then. His early training was in medicine, but he dropped out. He obviously had some mathematical training, and he measured motion of falling bodies, and through careful measurements, including work with an inclined plane and a pendulum. And from that, he was able to work out correct descriptions of projectile motion. So he was able to show that you had a parabolic path for projectiles. He was an early champion of experimentation to test hypotheses, so he was an early proponent of the scientific method. The thing he's probably most known for, well, two things. One is the motion thing, and the other is that he created a telescope. Now, he wasn't the first one to create a telescope, but he was the first one to really make better telescopes and to really make use of them. And from that, he made some observations. Among other things, he discovered there were 4 moons of Jupiter, which he could see with the telescope. Those are now known as the Galilean moons. That was, of course, the bigger ones. Jupiter has a lot more moons than that, but that's the bigger ones that he could see with its telescope. He also documented sunspots. Now, he privately supported the Copernican heliocentric model, and he ended up arguing for non-literal interpretations of biblical scriptures when a literal interpretation conflicted with observed data. Ultimately, his views got him in trouble with the church, with the Inquisition, and he was condemned to imprisonment. Luckily, they basically condemned him not to a prison, but to lifelong house arrest because of his views. But because of his work with telescopes, astronomers then had another tool to make much more accurate and interesting observations. Think about that. All of the astronomy we've talked about before Galileo was done without telescopes. Now that brings us to Johannes Kepler. So Kepler was born in 1571 and died in 1630, so late 16th, early 17th century, in the Holy Roman Empire, which would be currently Germany, where he lived. So he was a German mathematician and astronomer. He worked on a variety of different things. He worked on optics, regular polyhedra, spear packing. He gave the first proof of why logarithms work, and he worked with volumes of solids of revolution. One of the things that led him to that, he was at his wedding, his second wedding, and they had stuck rods into barrels at an angle and were able to tell how much wine was in the barrel. He said, "Well, how does that work?" So he was able to work that out with volumes of solids of revolution. That actually, now from our current perspective, we can see that that may have actually uh, led to some of the discoveries of calculus a bit later. Now, he worked with Tycho Brahe. The last 2 years of Tycho Brahe's life, uh, Kepler came and worked for him. So he was making those and made astronomical tables. He compiled the work of Tycho Brahe over 38 years, along with his own work. And from that, he was able to create the best and most accurate and most complete astronomical tables up to that time. And he embraced the heliocentric model of the universe. So he was a Copernican in that sense. And by a lot of calculations, over 1,000 pages of calculations with Mars, he was able to discover that the orbit was elliptical. The first assumption was, like Copernicus, that it was circular, but then the data didn't really agree with that. So it took him many pages of painstaking uh, calculations by hand, and he was able to discover that the orbit of Mars is elliptical. Well, once he did that, he said, well, what if all of them are elliptical? So his calculations went a little faster for the other planets, and he was able eventually to show that a model fit very well by using elliptical orbits. This is what we still know to be true today. And from that, he was able to derive his three laws of planetary motion, the first one being that they had elliptical orbits. Later on, he was able to use logarithms to aid in his calculations. He didn't come up with logarithms, but he was able to use those. And some folks said, well, nobody knows why these things even work. Um, you need to, why would you even use these? And so he actually proved why they worked and then used those in his calculations. So that brings us to another mathematician, John Napier, lived from 1550 to 1617 in Scotland. There may have been some other variations on the spelling of his name. That's the modern spelling, probably not what he actually used. But he invented logarithms, and specifically, he was trying to ease computations with trigonometric functions. And one of the things, he had a physical device that he used that were rods with numbers on them, these little numbering rods that he could move back and forth. And they were made of ivory, so they got the nickname Napier's bones. So logarithms in general were then referred to as Napier's bones later, and of course the actual physical instrument. His logarithms were a little different than the version that we have today, but they had the basic idea. And then toward the end of his life, he was convinced that he needed to change that to make a base 10 logarithm and make them act basically like they do today. He wasn't able to complete that work, but Henry Briggs picked that up. Henry Briggs lived from 1561 to 1631, and Henry Briggs made the modern base 10 common logarithm tables. Those drastically reduce the amount of work and calculation that folks had to do uh, in doing some of this astronomical work, which took just like I said, 1,000 pages for Kepler just to work on uh, the orbit of Mars. And once they got the logarithms, that cut that maybe in half. So it really cut down the amount of calculations a lot. So that was turned out to be a very important calculation tool. And of course, we don't use them as much commonly anymore to do calculations because we have calculators, but logarithms are still important theoretically for several different things as well. So logarithms are still used to this day. So in summary, In the Renaissance, we had a lot of uh, advances in mathematics and in science. In particular, we had some advances in astronomy, leading to ultimately the final acceptance of a different model of the universe, that the sun was at the center of the universe, or at least center, now we'd say center of the solar system, rather than the Earth. And so that was a huge thing that took quite a bit of time for that to occur.